This video is going to be the first one in a series I'm going to do about group theory. And the group theory I'm going to look at is mostly going to be sort of aimed towards, well, it'll be aimed towards essentially chemistry, which is point groups and things like that. So lattices and then, the symmetries of molecules and stuff. But I'm going to go into a bit more sort of, I guess, abstract group theory than what you would probably get in like an inorganic chemistry class or something like that. So this will be applicable to other areas as well, even if you're just interested in group theory as, kind of its own sort of pure kind of abstract mathematics. But it'll be stuff that can apply to other sciences as well. But just bear in mind that, sort of chemistry and things like that are kind of the impetus for making this playlist. But this video in particular, I'm going to sort of situate group theory. So, like what is group theory, and where is it placed in sort of mathematics. And so for that, I'll be looking at algebraic structures. So that's the sort of title of this video. And so a lot of you know people who talk about algebraic structures start with what's called a groupoid, but I'm going to start sort of even more, I guess, basic than that, and that would be set theory. So a set is a collection of elements, and so I guess, even more basic than sort of axiomatic set theory would be naive set theory, which is just, a set is just a group of things. It's very arbitrary. You could say that there's a set that's, the tree outside my window, and some guy named Phil on the other side of the planet. That's a set of something. Uh, and the reason I wanted to talk about set theory was mostly because I wanted to look at some of these sort of symbols that often come up in set theory, and therefore often also come up in group theory and different algebras and math in general. And so we will look at a few of these things. And so the first one here, so this upside down A is the universal quantifier. And so it can be read as for all. And so that if we are saying that, X is it's like xi are some elements of a group, and then we put this symbol here, we're saying for all of the elements of that group, where this is sort of backwards. E is the existential quantifier, and so that would be something like this. So like there exists an X sort of inside our set, and so it's sort of picking out maybe a specific X, where the upside down A, the universal quantifier, is talking about all of the X's. Then so this arrow here is the material implication, and I actually have a playlist, a different playlist where I talk about logic and things like that. So you'll see a lot of these symbols in logic as well. And logic is kind of the way of trying to make language into something very mathematical, and so that's why you see a lot of these things here. But the arrow is essentially the if then statement, where the thing before the arrow is the if, the thing after is the then. So if you see something like this, it says if X then Y, and that means, if X is actually true, then Y is also true. And there is also the modus tollens, which if X then Y, if Y is not true, then X is also not true. Then the sort of triple equal sign here is if and only if, and so that means sort of X and Y. If one of them is true, then the other one is necessarily true, and if one of them is true, then that's sufficient for the other one to be true. And so that's why you oftentimes see it as well as these sort of two-sided arrows, because it's saying that if A is true, then B is true, but also if B is true, then A is true, and so it kind of works both ways. And then you'll see these two symbols here for the negation, which just means not. Uh, so I have this example here. If P meant blue, then this symbol with P would just mean not blue. So it would just be saying that, some object, you're not saying specifically what color it is, you're just saying that it's not blue. And then there is this sort of pointing upward symbol here and this pointing downward symbol here, where the first one is for and the second one is for or. And in this case, the or is the inclusive or. And so if you see this right here with the sort of downward pointing one, it means either A or B or both A and B. And so it can be inclusive for that. And then so these curly brackets like this are used to denote a set. So if you see something like this, with A, B, and C, that means it's a set whose elements are A, B, and C. Then this little symbol here, this one is one you see a lot. And so if you see something like this, it means that A is an element of some set M, where capital letters are often used to denote sets, and lowercase letters are for elements of a set. Then this sort of big U here means the union of two or more sets, where if you see something like this, it means the union of sets A and B. And so what that means is essentially if we have, say, this set here, which is A, and this set here, which is B, then the union of these two is some set C that sort of, contains both of them. And so this I'm showing as disjoint, but it could also be something that looks like this, where we have A here and B here, and then the union is sort of, everything inside here. Then sort of the upside down version of that looks like this is the intersection, where if you have something like this, like A and B, then this little part here is the intersection. And if you have this, so if you have A and B, then there's no intersection there. And so we would say that the intersection of them is this, and what that is the empty set. The empty set, and so that just means a set that has nothing in it. But sort of backing up here, we have this symbol here, which is the subset symbol. And so I'll draw that down here since I've kind of taken up my space to the right. So if we have that set, and then there's that set in there, where we have the set A here. Actually, I think I have it written the other way in the description. So, so we have A in here, and this is B, and so we say that A is a subset of B. And then you can see this crossed out one here, which means that it's not a subset. And you will oftentimes see this as well, where you have this subset symbol that doesn't have the line under it, and that just means the proper subset, where and I'll get into that in future videos a little bit more, but a proper subset just means that you're not counting B as a subset. So you can often say that that B is its own subset, that B is its own subset, because a subset is just something, as we'll see in the future, that is something that is elements inside of a set that sort of make their own set. And you can sort of quote unquote improperly say that B is its own subset. But anyway, those are the two versions of that you will see. Then this backslash here, so if you see something like this, it means the set of all members of A that are not members of B. And so if we look at our our Venn diagrams here. So we have A and we have B. So if we have this, it means the set of all members of A that are not members of B. So it would be, you know, everything here, just not obviously in B and not where A and B overlap. And so that's what that means. So there's also this one here. So I haven't encountered this one that often, but this is the symmetric sort of version of the slash, and it just means that all the elements that are only a member of A or of B, and so that would be, you know, something like this, A and B, and so it could be everything in here or everything in here, just not the stuff where they meet. So then you'll see this little cross here, and you know, and this kind of gets into one of the things that like set theory and group theory can kind of become confusing with, is this use of symbols that have a different meaning here than they do in our usual sort of everyday math. So when in our everyday math, this little cross like this means multiplication, but here we're talking about the Cartesian product. So it's a sort of specific type of function. And so what that is, and so we have this set big A, which is A, B, and C, then the set B, which is D, E, and F. And so we take the Cartesian product, and it just makes every pair of each of the things in both of those sets. So it's almost like you're doing a FOIL. So if you take an algebra like first, outside, inside, last, it's like you're taking these two sets and doing that for each element, so that you end up with a pair of each element. Well, you end up with each element in each set being paired with each other element in the other set. And that's what the Cartesian product is. Then there is the power set, which is just taking this set A and that we have right here, and then sort of taking every element of that and sort of pairing them with themselves, or even not just pairing, but grouping them in every possible way. So it gives us the empty set, it gives us each thing individually, it gives us each thing in this set together, and then it gives us this. And of course, if this was a set with 4 members, there'd be even more. And so the power set is sort of every possible combination of things inside the set becomes an element of the power set. And so those are some of the things that we will be running into in this video series on group theory, and I'll explain these things again when we get to them in later videos. I'm not going to assume that you just have all of this stuff memorized, though also I will be posting the lecture notes in the description down below if you wanted to look at this in a little bit more detail on your own. Then there is the axioms of the Zermelo-Fraenkel set theory here. I'm just going to go through these really quickly. So you can see that there are links on these. So if you look at the lecture notes in the description, it'll be in a PDF form. You can click on these links and it'll bring you to the Wikipedia page that sort of explains these things in more detail. So the first one is the axiom of extensionality, which says that two sets are equal. They're the same set if they have the same elements. And so that's essentially saying if we have, you know, this set here that's A, B, and C, and we have this set here that's also A, B, and C, that we're saying that set A and set B are the same set. Then there's the axiom of regularity, which is one of those axioms that doesn't actually get talked about very often, and it's mostly just to avoid what's called Russell's paradox. And so it just essentially what it comes down to is that no set is an element of itself. And so, Russell's paradox is the set of all sets that are not members of themselves. And so that brings up that paradox there. And so this axiom of regularity, which doesn't really come up that often in a lot of mathematics, is just mostly to avoid that paradox. And then so the axiom schema of specification. So given a set A, there is a set B, so a subset of A, such that given any set X, X is a member of B if and only if X is a member of A. And so essentially what this means is we have our, sort of this nested hierarchy of sets. We say that this one in here is X. We say that this set A, well, I guess that one's the big one here. This is this one. And we're saying that if set B is a subset of A and X is an element of B, then X is also an element of A. Then we have the axiom of pairing. So if X and Y are sets, then there exists a set which contains X and Y as elements. So we're saying that we have a set here and a set here. They're both different sets, but then we can define another set here that actually contains both of those sets. The axiom of union: for any set of sets F, there is a set A containing every element that is a member of some member of F. And so that's essentially kind of what the example I have here is. So if we have this set here, that's a set of sets. So it's a set that has one of its elements is this 1, 2, another element is this set 2, 3, another element is this set 3, 4. We can specify another set A that just has each of the elements of these subsets once. And so we have this set A, which just contains once each element of each subset of this larger set F. Then we have the axiom schema of replacement. So the image of a set under definable function will also be inside a set. And so that gets into sort of the theory of like functions, where if we have some set here, then we have this function that maps every element of this set. Then when that mapping will take those elements into another set. And so the sort of if you want to think about this in sort of mathematical terms, if this is our independent variable and then this is our dependent variable, and something like y equals mx plus b, we're saying that when we take all the elements in set X and map it using this mapping, then sort of the answers will be these numbers that all are allowed to go into their own set as well. Then the axiom of infinity, which so it's basically just this successor notation where we can define 0 as the empty set. So it's just a set with nothing in it. Then 1 is the empty set union with the set of the empty set, and so on and so forth. And so this is sort of the way that sort of the natural numbers are sort of defined in set theory. So in set theory, you have to remember that everything is a set. Even our usual numbers that we talk about are sets in set theory, and so this is just using that to show essentially that you can count to up to infinity just using sort of sets that are inside of other sets that are inside of other sets, and so on and so forth. The axiom of power set: so for any set X, there is a set Y that contains every subset of X, so that's just the power set thing that I talked about above. Then the well-ordering theorem, which I don't think this is actually an axiom, which is why it's called a theorem, but it's kind of an important one, and it's essentially just talking about a relationship where you can say that X is less than or equal to y. And this will be true of sort of every element of your set. So you have a set that has, so many elements. And for each element in the set, you can define a relationship like this. And so this is keeping it even more general, where we can just say that, x R, where R is whatever relationship Y is something that well orders the set. But the one that kind of makes the most intuitive sense, I think, is like you know, the set of, all numbers. For all numbers, you can take any two of them, and this relationship here will hold between any two of them. Obviously, equals if both of the numbers are the same, but for every two numbers, one of them is going to be equal than or greater than one of the other numbers, and so that's kind of what that is. But anyway, that is a very non-rigorous sort of description of set theory, which is in the way that I'm sort of talking about this, the most sort of basic form of like mathematical objects. And so the next one up is what is called a groupoid. And so this is a set, but now we have a closed binary operation. And so closed essentially just means, so we take two elements of our set, we perform this binary operation, and it gives us another element of the set. And so that means it's closed, which so when you do this binary operation, you never get some element outside of your set. And so a binary operation is just one that takes two elements and does something to them. And so the one that probably makes the most intuitive sense would be just addition. So if we have 1 plus 1, that equals 2. And so this plus here is our binary operation. So you can sort of take, any numbers, so like this, where these blanks can be numbers, and this will give you another number. And so, if you take any natural number, so any sort of positive integer, and you add them together, you will get another positive integer. And so that is what the binary operation is. And closed just means, like I said, if you take any two members of the groupoid, I guess, and you do the binary operation, you get another member of the groupoid. And so this is, very general. And by that I mean everything that comes after this will be a groupoid, but then it will also have further structure added to it. But this groupoid is the one that has this closed binary operation. And so it, one that might be a groupoid but doesn't have the other structure would be sort of adding of binary trees. And so if you have like a tree that looks like this, where there is, sort of splits at these nodes here, and then you add another one like this, say something like this, what you're doing is you're essentially adding this further node up here that goes down like this, and then now we start with our other two like this. So this one is kind of going right there, and then this one is kind of going right there. And so this would be something that's kind of an example of a groupoid. So then a semigroup is one that now has this associativity, which means that if you have A, B, and C, and you do the binary operation on B and C first, then with the product of that, you do the binary operation of A with that product, is the same as doing the binary operation of A in B, and then taking the product of that and doing the binary operation then on C. And so the example that comes to my mind, since my background is biochemistry, is the concatenation of base pairs in DNA. So we have these base pairs here. and say these are, all just sort of separate from each other. If we concatenate these 6 of them first and then take the product of that and concatenate them with that, it's the same as concatenating these ones first, taking the product of that, and then concatenating them with that. And so the thing to notice here, though, is that we do not have commutativity, so it's not commutative. Where commutative would be if we could say have a have A, B, C like this, and have that be equal to B, C, A, or even just A, B being equal to B, A, where we see, if we sort of moved this over to the other side of the CGT, then we would not get the same string of letters, the same string of base pairs here. And so this is not commutative. You can add commutativity, but commutativity is one of these things that until later structures is this thing that's sort of optional. And in fact, we'll see when we get to groups that commutativity has a special name. They're called abelian groups, where non-commutative are non-abelian groups. So the next structure up is what's called a monoid. And so this adds a two-sided identity. And so I specify two-sided because there are instances where you could have like an identity like this that gives you A, but it wouldn't work if you put it on that side. But a monoid has this two-sided identity where you perform the operation from on your object here, A, from either side, and it just gives you A. And so that's what an identity element is. And so in math, in sort of our everyday math, with addition, if addition is our binary operation, the identity element would be 0, because if you add 0 to anything, you just get the thing back, or 0 plus 1 equals 1. So it works from either side. So multiplication, obviously 1 would be the identity element, where anything times 1 is just the thing itself. And so that is just what an identity element is. And the identity element sort of opens us up to further structure, which we find in groups. And so I put that in red here because this is kind of the level here that I'm going to be mostly talking about in this series of videos. And so this has 4 properties that make it into a group. So the first one is our binary operation here, which actually just comes from the fact that a group is sort of a more specific, a more structured version of a groupoid. So it possesses what's sometimes called the group property. So it's associative. So it also has that semi-group thing onto it. It contains an identity element. So that's where the monoid thing comes from, but then it also adds this number 4 here. So for every element R, it contains an inverse, such that doing the binary operation with R and its inverse gives you back the identity element. And so this would be something like we'd have to go past the natural numbers now to the integers, which are negative numbers, or negative, like -1, -2, -3, and so on. It contains 0, and it contains all the positive numbers. So the negative numbers are the inverses of the positive numbers, where, like I said, 0 is our identity element. So you do 3 plus -3, and that gives you your identity element. And so that is what the inverse means. And if you wanted to do this for multiplication, which you actually wouldn't be able to do here because groups don't have multiplication defined on them, but the inverse of multiplication is division, as we will see here in a little bit. And so this is what a group is it has all three of the things from these earlier parts here, plus this inverse on here. And I'll be talking about, in the next few videos, sort of, what all these things mean, sort of, all the things you can kind of do with this, in sort of to help sort of define better what a group is. And then after that, I will be talking about, I'll be getting into things like point groups and things like that. So that is kind of the level that we will be talking at. But we can go further past groups, and I'm going to kind of go through these fast because this video is already getting kind of long, and we're not even really going to be talking about these that much. So a ring, now we add this other closed operation. So we first had just this plus on it, but now we're saying that we have this plus and that the plus is commutative. But now we're also adding this multiplication, which is non-commutative, so it's non-abelian. So the operations are distributive. So if we have the addition inside parentheses here, then we do the multiplication. The a just gets distributed to both of them. So the division ring, so the second non-abelian group operations now have an inverse. So that would be like our multiplication and division. So we get back to 1 in multiplication. So if we have a and say our inverse is something like 1 over a, which is the same as a to the minus 1, is equal to a over a, which is equal to 1. And so a division ring is bringing in division into it. So then a field, so this is where the real numbers are. So now both binary operations are abelian or commutative. And so that gets you into sort of like the math that we sort of all know and love, where we have addition and multiplication, and then their inverses, which are subtraction and division. They're associative and they're commutative and they're distributive and all those things that you learned in early algebra classes. Then we have our modules, so it contains our group and a ring. So we essentially have two different sets of objects that we can pull from, and then we define these mappings where so the mapping of our ring in our group gives us another element in the group, and this works both left and right. It's distributive and associative. Then we get to vector spaces, which now contains a group. Instead of a group and a ring, it now contains a group and a field. And so in vectors, you often learn about like the scalar. So you have like the c, and then you multiply that times your two vectors here, and that gives you c times a plus c times b, where the c is just scaling those vectors. And so I took this from Wikipedia. This is sort of all of the things that are used to sort of define a vector space. And then we finally get up to an algebra, which then sort of adds vector multiplication onto it, where you see up here we only have vector addition going on here. There is the scalar multiplication, but then when we promote ourselves up to an algebra, we now have this vector multiplication. So it allows you to do things like the dot product and inner product and things like that. But anyway, like I said, we will be talking about groups in this video series. Later we will get up to talking about vector spaces, but for the most part we'll be talking about groups in this. And so these four things, which I will review again in the next video, are kind of the things we have to remember for a group. It has this binary operation, it has associativity, it has an identity element, and it has inverses. But anyway, I hope you found this video helpful, and I will see you in the next one.